Okay, assalamu alaikum and good afternoon, everyone. My name is Tariq Nafouri. I'm an associate professor of electrical engineering here at KAUST, and it's my pleasure to welcome you today and also to introduce our speaker. Our speaker is Mohamed Norain, who's a senior embedded systems engineer at Schlumberger Center of Excellence in Houston, Texas. Mohamed Norain obtained a master's degree with distinction in embedded systems from Heriot-Watt University in the beautiful city of Edinburgh in the UK. In 2011, he obtained the highest Sudanese prize in scientific innovation and creativity. Today, he's going to talk to us about his passion for embedded systems and the journey that took him there. So please join me in welcoming our speaker.
Assalamu alaikum. Hello, everyone. Early January 2017, I decided to share some of my life experiences with the people, and I thought that these experiences might inspire other people to change their lives. At that time, I had an average Facebook account in which I would post a post and I get maybe like 30 maximum interactions. Today, and after I post all these stories, I have like 12,000 followers in Facebook. And also I decided to create a group in which other people could come in and contribute their stories so as to even inspire more people. And this day we have like around 37,000 members in this group of active people actually sharing their stories, how they moved from zero to something, and how they obtain success by their own measures. And I think the number one cause of my my transformation was that finally, after some struggle, I found my passion. And my passion is embedded systems. In 1998, I was a school dropout. I decided to quit school in my secondary school because I thought it's not fun. So I completely stopped, went to the street, worked as a laborer, and then at some point, I decided to come back. Not only come back strong. And I moved from that to setting to like the secondary certificate, which it's done like throughout the country. I got one of the top marks or scores in the country. I joined the highest college in the country, and I moved after that to actually enjoy success without feeling the pain or the effort. And I think the main reason of that was embedded systems. And let me today share with you a just glimpse of the fun that I'm having with embedded systems. So, embedded systems is actually centered around microcontrollers. And let me give you just a simple explanation about what is microcontroller is. So the microcontroller is like a microcomputer, and it is exactly the same like, let's say, our well, not exactly the same, of course. It's something like our brain, something that will process information and does computation. But in order for that microcontroller to work effectively, it would need a way to sense the world around it. And the way to do that is through sensors. So sensors measure the real world and convert these measurements into something that is understandable by computer or by microcontrollers. Exactly same like our 5 senses. So it will be something like this. And today I'm going to share some of my YouTube videos in my home lab, which are fun. They might not make sense to most of the people, but they just bring me happiness, prove my theory, and I just enjoy them. And then after that, we are going to do like a real-life demonstration here for an experiment that I call it 15 and 15. And the reason I call it that is because I always run this experiment to show other people that embedded systems is not that hard. It's easy, cheap, pleasure, and fun. So, and the name 15 by 15 is coming out from easy and cheap. It's easy that it can be done in 15 minutes. After I explain it to you, maybe in 30 minutes or so, you can do it in 15 minutes in your home, and it will cost you $15 only, or less. So let's go on and watch this small machine here that I built. It took me some time and some effort, some sensors, microcontrollers, 3D printing, all this work. I just wanted to slice a banana. And I had to eat a lot of bananas in order to make it work up to this point.
we begin?
Let's begin now. Let's begin now.
Okay, so in this machine, basically I use two types of sensors. If you notice the Legos, so the Legos, I'm using them to adjust the thickness of the cut. And I have a digital sensor there that will sense whenever we have a Lego in front of the sensor, it will stop. Whenever that Lego passes, it will stop again, and it will keep doing that to adjust the thickness of the cut. So digital sensors, they have two outputs only, either 1 or 0. These are the simplest kind of sensors. And maybe the most common ones, the ones that we use in the water faucets, right? It detects that either your hand is there or not, 1 or 0. They call them digital sensors. And normally, these would require minimal interface between between the sensor and the microcontroller. So let's move on to another type of sensors, which is analog sensor. And if you noticed, in my machine, I had this knife, and there was another sensor connected to the joint of the knife. So that sensor returns the current angle of the knife at that moment, and it returns it as voltage, right? So for simplicity, let's say it starts from 0 volt at 0 degrees and 3 volt at 90 degrees. So you will, and it will give you a value, which is an interpolation of that in between. And these analog sensors, which the one I'm using, they're exactly the same like, the old radio volume potentiometers. So it will provide an analog signal, and we have a small machine in our microcontrollers called analog to digital converters that will digitize these values into numbers that the computer could understand. And by using that, now I can get the measurement of the angle, and I use a PID controller to get the angle and then adjust the speed of the copter so as to stabilize the knife at a specific angle. Otherwise, the knife, for example, if I turn the copter too fast, it will just fly to the other side. Okay, let's go to another machine. And again, these machines, they're just for fun. The M&M sorting machine. Okay, if you noticed in the video, the machine will not, it's not very accurate when is the next blue M&M will come out, right? So I had problems with that at the beginning, because what I wanted to do, I wanted to be looking at my computer, doing my work, and then, you know, just being ready whenever that blue M&M is ready to be thrown out. So I had to actually add a small light that is not visible here and add it in front of my laptop, right? And then whenever the color sensor detects a blue M&M, that light will flag and will tell me that, hey, the blue M&M is coming soon, be ready. And then I will turn on and get it. So the color sensor that I used here to differentiate colors has an output that I'm not going to discuss in the next slides, but it's just for those who are curious about it. It's a pulse width modulated signal output. Will give you the red and green and blue contents on the color as pulse width modulated signal. So next, we're going to look at two of the most common sensor protocols, sensor outputs. So far we talked about the digital ones, the analog ones, and now we are going to talk about the serial ones. And the two most common are the I2C bus output sensors and the SPI, which is the serial peripheral interface bus sensor. I'll talk briefly about each one of these. So the I2C is very easy to implement, very easy. If you are using the same tools that I'm using here, probably if you know the sensor very well, it will take you maybe like 1 hour to actually write something that works and give you an output from your I2C sensor. And the reason I'm saying if you use the tools I'm using here, and I'm willing to share it with whoever is interested after the speech, but these tools here would do the basic setup that you need, the boring side of the work, you know, the basic configuration and setup for you. And then you can just enjoy the output after that. It will generate the code ready for you, and you can just execute it after you add your user code, like what you want to do with these color values, right? The I2C bus, people likes it because you only need 2 lines to connect your sensor to the bus. You will have a master, and it can be one master, or it can be several masters, and it's half duplex protocol. And when we say half duplex, that means you are either transmitting or receiving at the same time. You cannot transmit and receive at the same time. And normally what happens here, the master will drop a message in the bus and say, hey, sensor number 1, I want to talk to you. So now all the other sensors will keep quiet. Only sensor 1 will talk to the master. And then after some time, the master will say, sensor number 2, I want to talk to you. Then all the other sensors will know that this message is not for them. They will just step out. So I2C is good, but it's designed for lower data rate. Most of the time, it's 100 kilohertz to 400 kilohertz. And now we started to see some megahertz new I2C speeds. And it's also for short distances, so you cannot make it like for, I would say maximum it will be around 1 meter. That makes sense. So it's designed for things that are sitting together very close to each other. Okay? Then we have the SPI protocol, the serial peripheral interface protocol. And in this one, you have the master will have one line, which called the slave select, going to each sensor. And whenever the master wants to talk to one of these sensors, it will send a message on that line, send the voltage level on that line, so as that particular sensor will talk to the master. And it will use the other 3 lines to do the communication. It's a little bit faster than the I2C. You can transmit and receive at the same time. And normally, It's not as famous in the sensors world as the I2C. You'll find it more in other peripherals like memory. And okay. So I think this will end the theory part of our presentation. Let's go to our experiment. So in this experiment, I'm basically using an analog light sensor. After the experiment, I would pass it around if people want to have a look at it. So basically, I have a small development board that I bought for $8.9. And I have a sensor that is for, I think, $2 or $3. And then you need small connectors to connect the sensor to the development board and a USB cable to connect it to your machine, to your PC. Now, in your PC, you will need also 3 softwares. First software, it's a graphical user interface called STM32Cube, and it will help you to generate the boring side of the code, configurations and everything. And it will save you a lot of time, basically. You don't need to, every time, to initialize and configure things manually. So that software will help you to generate the code. Then you have an IDE, Integrated Development Environment, which is Scale, and I'm using it to add my code to this automatically generated code and download to the microcontroller. Okay, finally, I have another software to visualize the variables as the microcontroller running. And this is how we are going to see how the light in this room, the measurement of the lights in this room will change as we actually turn on and off the lights. Okay. So this is the software that displays the current light intensity in this room, okay? And the code for this one is literally the code I wrote, and I would love actually to show it to everyone, because it's 3 or 4 lines of code. That's it. So the code we wrote for this experiment is exactly these 1, 2, 3, 4, 5 lines. That's it. Okay, so now you see, as we change the light here, this value is going up and down, right? So let's just do a drastic change on the light. Why not? Okay, that's good. So finally, one last thing I want to say, actually, is don't live other people's life, right? Just try to really find your passion, and you will find ways to enjoy success. Ladies and gentlemen, it was a pleasure to talk to you today. Thank you very much for your time, and I hope to see you again in the future. Thank you.
Thank you very much, Norain, for your talk. Now I open the floor for Q&A.
So I will be here also afterwards if someone wants to come and ask me about these tools I'm using, or you want to see the sensor or the circuit that I have here.
Okay, so maybe I can ask you one question, Norain?
Yeah, of course.
First of all, the lab that you're showing, is this where you work at Schlumberger?
Yeah, so this lab, actually, it's in my house. And, you know, it's a problem because I spend most of my time in the house in that room, right? So, you know, I have 2 kids. Well, now I have 3. just one like 2 weeks back. And just to spend even more time in my lab, I created a small area in the lab, inside the lab, for the kids to play in, so I could watch them while I'm working on my stuff. So yes, all this stuff is in another room in my house.
And another question, I mean, you mentioned that you worked as a laborer and then you decided to go back. I mean, what's the thing, what happened where you discovered your passion?
Actually, that's a good question. I was working, when I was a laborer, I was working with an engineer who was one of my relatives. And basically what he does, he fixes AC systems, okay? These ACs where you can control the temperature and everything. So I spent some time working on that, and I felt like I enjoyed it. Basically, I wasn't doing anything fancy, right? Because all the fancy work will be done by him, and my part of the work is just probably, take the AC out, clean it out, repaint it, and everything. But meanwhile, when I'm done with that, I'll be sitting next to him and see what he does. And that's what really actually just felt like, okay, I have to go back. This is not working. Okay. Yes.
Thank you very much, Mohamed, for the talk. When you designed the banana slicer, I realized that in addition to sensors, you had quite a bit of additional mechanical component. You had a propeller. You had other things. So in addition to sensors, maybe you invested some time into figuring out how big that propeller needed to be, and
yes.
Maybe some other design considerations. Can you talk a little bit on how you put those things together? And now that I have the microphone, before I return it back to Tariq, maybe you can tell me a little bit on how you actually code the code that actually microprocessor that takes those signals, from languages, and how difficult would be for somebody in fluid mechanics like me maybe to get a little bit of contagion about your passion.
Okay. Okay. So for the first question, so the question was, well, you said embedded system, but that machine involved other stuff, involved mechanical and control, right? And I would say yes. Sometimes you have to go through things that you don't really like to reach to the part that you enjoy, right? So it's not always, okay, when I say fun, probably the fun just comes at the end or at some points while you are building your machine or stuff, right? But definitely, the way to that fun, in the middle, you have to push yourself through some theory, some stuff that you are not very interested in to reach to that point. And to do this machine, actually, I had to go back. I wasn't very good in control. Well, now I'm not very good in control, of course. Nobody's very good in control. But I didn't know a lot about control and at the beginning. Then I had actually to take a course, maybe for 20 days, to be able to control the propeller smooth enough so as it will stand and just stop, and go down. I had a lot of failures where, my coefficients wasn't right, and as I'm progressing through the course, the control theory, every time I would go back and tweak a little bit, go back and tweak a little bit, and the moment it works, I'll just dump the course. So I'll take as much as I need to run my experiment. And as you do that by time, now next time I do a project that has a PID controller, and it was funny that after I did that, immediately, I had a project in Schlumberger which needed a PID controller. So it was very easy after that. So that was the first question. And for the second question, let me just give you a quick, I think the best way to answer this question is just to show you these 3 or 4 lines. Okay. So it's very it's very logical. You don't really need to write a lot of code most of the time to do simple stuff. And what I try to do always, and I think everybody should try to do, is try to utilize some code that already exists ready for you to use, right? So looking here at the code, it's very logical flow, okay? So as you see here, the first line here, what I'm saying, I'm asking the analog to digital converter to start converting the signal that is coming from my sensor. Here, analog to digital converter starts, okay? And then I am waiting for it, pulling for it. So you will wait for it for a maximum of 100 milliseconds, and it should be done by 100 milliseconds. If it is not done, then there is something wrong. So after 100, during that 100 milliseconds, it will finish the analog to digital conversion, and if it finishes correctly, then it will reply to me and it will say, okay, like I am done, within the 100 milliseconds. If it didn't finish, then it will reply and say no. And I have to, consider error. We're not considering now how to handle errors, because I'm sure things are working now. But anyway, if it says okay, then what I'm going to do is I'm just going to get the value and store it in a variable called light, okay? And then after that, in order to make this not very fast, because the light doesn't change very fast in the room, I'm doing this every 200 milliseconds. So I'll take a delay of 200 milliseconds and start this process again, right? The other software here, we have this one, which displays the value. All it does is it actually just displays the value of that variable called light as a column here. That's it. So yes, trust me, it's very simple. For most of the basic stuff, you don't need a lot of computer science background. You might stuck at some points where you need some explanation or help or take a small course, but it's definitely doable.
Okay.
Yes.
Thank you. I wanted to throw it so much.
Good afternoon. In first place, thanks for the talk. It was really interesting.
Thank you.
I have a question about. I'm curious about which kind of 3D printer they used in your experiments, because I see for some components that you design your own 3D things and you print by yourself. And after that, for a beginner, which kind of 3D printer do you could recommend us for starting some projects?
Okay, good. So actually, I really like this question because I suffered a lot until I reached to the answer that I'm going to give you now, right? So my theory, normally, I don't buy expensive stuff. I buy as cheap as possible so I could keep buying stuff in my lab, okay? And this theory sometimes will cost you a lot of headache and time, okay? So at the beginning, what I did with the 3D printers, I bought a 3D printer, a cheap one, and I spent maybe $250, I think up to $400 on the printer, on the 3D printer. And then I would print with average quality, something, and then I will need to work maybe the printer will work 3D printing for half an hour, and I would work on the printer for 1 hour to make that thing work, right? Because every time you need to adjust this, remove that, take this. So I spent a lot of effort and time. And then finally I decided, okay, I'm doing this for life. I know I like it. It's better that I invest some money and buy a good 3D printers, right? So I bought one for $1,800. And since then, I'm not spending any time maintaining that 3D printer. I would just literally run it, an okay quality, as you see here, that does the job. And all I need to do is just change the ink, which is these filaments. So you don't need to buy an $1,800, but I would say at least $500. Meet me after the talk, and I will give you a link for a good one. Okay? And you can buy it even for cheaper than that if you are willing to put it together yourself. Okay. You had another question, right? Did you had another question? Okay, you said which one is recommended. I already answered that one. Okay, yeah.
Yeah, we have a question there.
Yeah.
I guess first off, thank you for the talk again.
Thank you very much.
So one thing that always bothers me when trying to program microcontrollers is where to start, given the amount of libraries and like scattered documentation everywhere. When you sit down, like I've written in Python, other high-level languages, but when I look at code like that and think, okay, where does HAL come from? Where are all of these like GPIO functions defined? Like where do you start when you write the software?
Okay. This is also a very good question because I also suffered a lot before I reached the answer that I'm going to give now. So I know we are curious creatures, right? We are very curious, right? But sometimes, in order to invest well on your time, you have to, force yourself to accept things as is, if it is proven to work. Otherwise, you are going to waste a lot of time, right? You say, if we have Ohm's law, it's a theory. It's given, proven, it works, right? I'll say don't spend long time to try to understand how they come up with this theory. Try to use it. If it works, then just keep building on it. Don't start from scratch, right? So these guys here, ST company, they spend long time preparing these lower level functions for you, ready there. So just use them. Use them. You know what you can do? Like for example, now in this code, you can pick up the name of the function, Google it, and you can find a small explanation about what this function is, how it works, what type of inputs you need to add to the function, what is the output that this function will give you. Plug it, try it. If it worked, just accept it as is. Try to do that. I know it's hard. Try to do that. Instead of spending hours in trying to figure it out, spend these hours on building on top of it. So start from where the rest finishes, right? Good.
Or another way of doing it is to attend a workshop like the workshop that Mohamed Norain is giving us this week. Today was the second day. So hopefully, like in the future, he'll come back and give us similar workshops. Well, please join me in thanking Mohamed for his talk.
Thank you. Thank you. Thank you.
And Mohamed, this is a token of our appreciation.
Thank you very much. Appreciate it. Thank you.